with you giving a presentation of 25 minutes or so, and then we have one internal examiner and 3 committee members, and 2 rounds worth of questions, and then keep your questions for afterwards. And I'll let Radina tell us her title, because I can't memorize all of that.
Thank you all for coming. So the title of my thesis is Segmentation of 3D Brain MRI Images Using Active Contours with Shape Priors. What I'm going to talk about first is the segmentation problem. I'm going to define that for you. Then I'm going to talk about Chan and Vesey's method, which is the main segmentation method that I use. Then I'm going to talk about shape priors, which is a way of incorporating shape information into the overall procedure for segmentation. I will give a brief overview of the full model, how everything gets put together. Then I'll show you some results. Medical image processing. So this is a tool that's been developed in the last few decades to help medical researchers to extract useful information from medical images. What I've done in particular is I've taken a brain MRI image. So this first one is just the raw data that comes from a brain MRI image. And then I have run my procedure to extract the eyeballs, so locate the eyeballs in the brain. So I've superimposed those. And the way I've done this is in sort of an automated way, so that you can actually process a large amount of images, so that you can run some sort of statistical analysis on whatever data you end up extracting, like the volume of the eyeballs or their size distribution, things like that. That would be very difficult to do by hand. So what is segmentation? Image segmentation is the problem of giving the computer some image and asking it to figure out where the object in the image is. So the way I'm going to define it is looking for a curve C, which defines the boundary of a particular object. So this is one example. So the red curve here would be the thing that we're actually looking for in the segmentation problem. So how do we define this in mathematical terms? How do we keep track of this curve C? Is I introduce a level set function phi, which I'm going to define to be positive inside an object, negative outside, and therefore a 0 level contour set defines this boundary of the object that we're actually looking for, this curve phi. The general approach that I'm going to take here is, because I'm trying to find a particular object in the image, I'm going to actually break up the problem into 2 stages. First, I'm going to incorporate some shape information about the shape of the eyeballs to find their approximate location in the image domain. Then I'm going to run a precision segmentation procedure on this relative region to get the exact precise segmentation of the eyeballs. So first, I'm going to actually start talking about the second step, the precision segmentation algorithm that I'm using here, just so that we can see what we can do with that and what we need to do before that in order to get the exact result that we're looking for. So I'm using the Chan and Vesey method for the segmentation. And what they do is they minimize this energy in order to find this curve. So they're looking over the set of all curves inside the domain, which gives the smallest energy. So to explain the intuition behind this energy, I have this picture here. If you look at picture 4, the blue curve is the actual boundary of the object. That's what we're looking for. If our curve happens to be that particular boundary, the correct boundary, then this energy will be 0. What is the energy? The first term is I naught at x and y. This is the intensity of the pixel at location x and y. C1 is the average intensity inside the current curve that we're considering at the moment. So if we're in this picture 4 here, this first term will be 0 because every single pixel in here is yellow. Therefore, their average is yellow. So that first term will be exactly 0. For the second term, we're looking at minimizing the variance of the intensities outside of our curve. All of them are white, their average is white, so the second term will be 0. If we look at picture number 1, the energy will be greater than 0 because the first term, all of the pixels inside are either yellow or white, but their average is some sort of light yellow. So if we look at the first term in the integration there in the energy, it will be greater than 0. And then the second and third picture show some other cases where the energy will be greater than 0. So it's important to just notice that it's exactly 0 in the last case, which is the one that we're looking for. We're looking for that curve. So what we're going to be doing is we're going to have some sort of curve that evolves according to this equation. And because we're evolving it in time, we need to make sure that it keeps smooth, it stays smooth. So we don't want to have any sort of jagged edges. If the image quality is low and the boundary of our object happens to be pixelated, we want to avoid that. We want to have a smooth curve. So we're going to actually, to that energy, we're going to add another term. That's a regularizing term, mu times length c. Mu is some parameter greater than 0. So we want to minimize the length of the curve, which will help us keep it smooth. So in order to be able to, so we want to find this curve phi, but remember we're using the function phi, the level set function, to keep track of our c. So in order to be able to minimize this energy with respect to phi, we rewrite it slightly. So notice that the integral inside c of something can be written as the integral over omega, which is the whole image domain, of the same thing times the Heaviside function of phi. The Heaviside function of phi is 0 everywhere except inside of our object. So that matches. So those two integrals are the same. So we rewrite this energy in this way. The length term now becomes just the gradient of the Heaviside function, the length of the curve phi. So the gradient of the Heaviside function, it only has a non-zero gradient across where phi changes sign from negative to positive, and that's exactly our curve c. So this is the equation for Chern-Vessey's energy. And the Euler-Lagrange equations, just the gradient descent, are these. Notice that the equation for phi is multiplied by the delta function out front of everything. The delta function is it's almost 0 everywhere except around the 0 contour of phi. And the 0 contour of phi is what we actually care about. Right, it's the boundary of our object. We have some initial conditions, some natural boundary condition that arises, and then we actually have a sort of nice expression for this C1, the average intensity inside of our object, in terms of phi. And there's a similar one for C2. I didn't show it because it's very similar. So these are the equations that we're solving. The purpose of my thesis is more of a proof of concept. So I just wanted to demonstrate that breaking this problem up into 2 stages will actually give us the result we want. So what I've done is just the simplest thing to discretize this equation to solve it. I've done a forward Euler in time, centered differences in space. And what we do is we calculate C1 and C2 at every time step, every iteration step. Notice that C1 and C2 are in terms of phi, so we have to calculate them at every step. We update phi according to its equation. And the stopping criterion could be one of 2 things. It would make sense to choose when the energy becomes approximately constant. So we're looking for a minimum of the energy, so when the energy goes down, we can check to make sure that it's staying the same, so that we've reached our minimum, we've settled down, so we're where we want to be. Or what I've actually done is I run this for a preset number of iterations. The reason why I do this is because it's difficult to choose a universal threshold value for when the energy becomes constant. But all the images that I work with are very similar to each other. So they're all an image of a brain that's been registered, meaning it's aligned to be the same direction, and it's reasonable to run a few experiments, look at when the energy is settled down, choose that number of iterations, and maybe increase it by a few just to ensure that it works for every single image of this type. And this is an example of an evolution of Chern-Vessey's method. So we start with some blurry looking objects. The red square in the first picture is my initial guess for what the segmentation is. And then I run this for a few iterations, and it finds the object quite nicely. If I were to go to iteration 100 or whatever, it will look almost exactly the same to this. One thing I wanted to show using this particular picture, because it's very blurry, is that Chern-Vessey's one of the benefits of using Chan-Investe's method as opposed to any other segmentation method is that it doesn't rely on having the object inside of our image to have sharp boundaries, clearly defined jumps in intensity, like if the background's white and the boundary of the object has to be some significantly different intensity. So it doesn't rely on that, which is good because some medical images have low quality and there's just not much we can do about that. So this would be, that is what we're going to use for the final stage of my method, the precision segmentation. Why can't we just use that on its own? Because if this is a 2D slice of a brain image, if we just run the algorithm on this image, Chan-Investe will find the whole brain as one object. And that is not what we want. We just want the eyeballs. So we need to find some way to tell the computer that we're looking for two objects that are circular, certain distance apart, and then find their location, then restrict our domain to that region, and then go back to Chan-Investe. And trust that we'll get the result we want.